So we are here. We're going to finish this problem up, and it's not well. Okay, it is pretty complex. There's a lot going on, but it's still though it's okay. We can do it, right? These are all second derivatives, and I want to remind us these have a Newtonian feel to it. I know they're using W. I'm going to do F. That's easy to do. F. This is X X Y Y. Which one would this be? Do you remember? X, Y, and then Y, X. Yeah. It is weird because, again, we're going backwards, right? And that is it's so bizarre to me. But that's why I write the Newtonian style, so that it's, better. So, yeah, all of these have a prerequisite of I have to do a first derivative. So let's do the first derivative of each style. I guess I don't need that calculator over there. If I'm doing it in terms of X, what would I have right here? In fact, what would I use for this whole thing? Yeah, I'd have to use product rule because there's an X thing here and there's an X thing there, essentially, right? I don't think that's going to be the same for the Y's, but definitely for X. So I'm going to leave the first alone, take the derivative of the second. Derivative sign goes to? Cool. Leave the inside alone of that. Take the derivative of that. Perfect. Again, only the X's. The Y's are technically like a number, so we don't really touch them. And then I take the derivative of the first, which is 2. Very good. And then I leave the second one alone, which makes it super easy. Sweet. So I know that looks a little bit, right? It looks a lot, Chad. I know. I don't know how to help it, but let's branch off. So now we're going to do XX, and then we're going to do XY. So for XX, I now need to take the derivative of this in terms of X. Oof. Yeah, that's how I feel. That's how I feel. So what I want to do just a tiny bit, I'm going to simplify this a tiny, tiny bit. Like right up here, notice that there's 2 X's right there. Now I can mush them together, right? 20x squared y, and then cosine, and then plus 2 sine. And I'm leaving the inside alone. We already know what the inside is. I'm just saying, like, we have this x squared out here. That's going to be our thing there. Yeah, we're combining like terms, basically, right? Those two guys. The 2 and the 10 make a 20, etc. But because I've done that, now I can see it a little bit clearly-ish. So I'm going to leave the first one alone. And I take derivative of cosine. Cosine will go to negative sine. Yep, very good. You got it. And we already found the derivative of the inside before, so just kind of copy-paste that. Plus, now I'm only looking at this first chunk here, okay? Just looking at the first chunk. Now I take the derivative of this piece over here, which actually not 20 anymore. Very good. 40 x, y, and then I have my cosine. I leave that alone. I don't want the parentheses around. I don't like the parentheses. Well, I just start over, Chad. Okay. Oh, man. There's so many parts right now, and I'm not even... We're not done. We're not done. We got more to go. So there's that other part. Plus, we have a third component. Now it's just that sine. It's this bit. I know, right? It just doesn't end. Whoa. So now derivative of sine goes to cosine. So I got a 2 cosine. Again, I have the inside to leave alone. And then I take the derivative of that, which we've done a whole lot of times now. This whole entire thing, The whole thing is XX. We've done 1 out of 4. Now, before I even touch that thing, what do they have? What does it look like? So they're trying to combine like terms. Notice that they're saying that you got your cosines and your sines. So cosines, one term, sines, the other. And I don't have to do that, but I want to look at it and see if I can, you know? So like this would be a sine, and these are both cosines. So if I look at just my sine right here, just this guy, I'm going to use different colors. Just looking right here at this guy. I have a negative. My number's in the front, that 200. So I'm already getting nervous. And then I got x cubed, y squared. What do they have? Oh, yeah. No, there's the sinus right there. 200 x cubed, y squared. Yeah, okay. Okay. See, they put it in the back because of minus. And then these two cosines work together. Again, kind of like ignore the cosine part. That's like the part that's common for them. It's all the other pieces we're looking at, right? So then I have a 40xy. And here I've got a 20xy. And so I'm doing like basically 40 plus 20 is 60. And that's how they get the 60 in the front. So, yeah, I mean, I'd rather just show you the answer and like have you copy that down because it's way cleaner. But confirmed we did it, and we did it right, but wow. Is there an easier way, Chad? No. Actually, no. I wish there was. In fact, the next section is going to be talking about easier ways to do this, finger quote, but the problem is they use different variables, and so it doesn't really match up. It's not the same technique, unfortunately. But it will get easier, essentially. I'm trying to say, like, yeah, this is tough, but going forward, there's better techniques for other questions. Very tedious, yes. Very, very tedious. And one little thing you get wrong, one minus sign, one little plus, one power. Okay, so we only did this one. Now we got to do XY. Now I got to say, I think this is going to be easier because the Y's have smaller amounts. There's not as many X's. But I still have to start with this big thing. So if I'm looking at this and I'm doing it in terms of Y, I have a product rule here, but then this will just be a regular derivative. All right, let me get a new color. So this will be my XY. So I'm going to take the derivative of the first thing in terms of Y. No, I'm going to leave the first alone. I keep doing that. I'm going to do that. So derivative cosine turns into a, see, I'm looking right there, into a negative sign, right? I'm going to leave the inside alone. And then derivative of the inside, we've done, oh, whoa, 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 whoa. In terms of Y, derivative of the inside in terms of Y, what is it? Very good, very good, very good. Yep, good. Good. And then plus, now I'm going to do this cosine deal. So I'm going to take derivative of this thing in terms of Y. And then I just write cosine, basically. Okay, and then plus, now I have to do the sine part here. And sine goes to, but then the derivative of the inside in terms of Y squared. Yep, very good, very good, very good. Okay, whew. So like that is the answer, but we need to like try to figure it out what we're doing here. We do a little bit of orange. So we got a sine, and that's the only sign. And then we have this one as a cosine, and this as a cosine. So these are going to be grouped together, and then we're going to have a sign there. So going back to the answers, they have only a sign, which is kind of freaking me out. But let's go and check it out, okay? So I only have this one sign. Are these just so happening to be equivalent and opposite, maybe? I don't think so. I got one that's positive, one that's positive. I'd have a 10. Did I mess up somewhere? I must have messed up somewhere. And this, I mess up too. I just want to remind you that, okay? It's, huh? Oh, gosh. What am I thinking? You're right. I'm doing XY. Is this dude? I'm doing this one. Oh. Thank you. I know. Man. Well, because I had the X start, but you're right. That's what they're wanting you to do. I wouldn't do that. I would say, first, second, third, fourth, in order. Mm-hmm. Yeah, yep, you're right. I did mess up. So these cosines combine together, and they all have an x squared. So that's 10 plus 20 makes a 30 for these cosines. So let's see. Do I have a 30 for my cosines? Yep, there it is. And then the other one I have 5 times 20 is 100. So yeah, I'm just going to leave that up there. Y'all should probably write down all 3 answers, all 4 answers, and that way we know where we're going. Because there's so many moving parts. Of course, please take your time. No rush in this class. Definitely don't want to rush. That's the perfect time for me to get coffee. I don't know what it is, but most of my classes do not drink coffee. They almost all did last semester. This time, nobody does except for statistics. Tuesday, Thursday afternoon. So y'all drink some, I see, but Tuesday, Thursday afternoon, right after the club meeting, and a lot of people at the club drink some coffee. So the one class that drinks it, there's never enough left, and it's the last one, so I don't want to make more. So sorry, guys. Oh well. Y'all tell me when you're good, and then I'll move over. Again, no rush at all. We're good here. And you wonder sometimes, is there like a commonality? Notice here that my XY and my YX are the same. At least they look the same. And that's a cool thing. That's a good thing going forward, but that's not a discussion today, I don't think. I don't know when that would come up. I'll talk about it in a few minutes. It's more like theory stuff. You just tell me when. We're good. Good? 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 You got it copied? You're good?
Oh, I'm still where
You're doing it?
Yeah.
Oh, okay. I mean, did you need this up anymore?
Oh no, I'm good.
Okay.
I'm just working it out.
Good. All right, so yeah, good with that. Now let's do the first derivative in terms of y from the beginning. But this should be much, much easier because there's only the one y component. All these x's in the front are acting like a number. So you just leave them alone. Sign goes to, leave the inside alone. And then again, the derivative of the inside in terms of y is yes, 5x squared. Very good. Yep. Correct. We're done. That was it. So that was easy, but again, that was only the first derivative. So then let's do the double y because it's going to be way easier, as you know. Because yet again, here I'm going to simplify it down a little bit. I'm looking to see how many y's we have, and it's only the one part of it. So when I take the derivative in terms of y again, negative sign. So yeah, negative 10x cubed sine of the inside. Derivative of the inside makes a perfect. That should do it. So notice the 5 and the 10 will make a 50, and there it is, 50. Much easier. Whew, finally. Got something good here. And now I'm going to take this and do my yx, which, as you know, is going to be crazy, but oh well. So I'm going to leave the first one alone. Derivative cosine goes to negative sine. Oh, it's not too bad? Okay. Yeah, the double x. Yeah. Derivative of this guy in terms of x. Be careful. Yes. Yep. And then I now take the derivative of the first one. So 30x, very good. Squared. Thank you. And then I leave the cosine, and I don't do anything else with it. Actually, we're done there. So if you combine like terms here, you would have 10 times 10 is 100. X4y. And there it is right here. Oh, well, they're the same thing. Duh. Yeah, it's actually easier that way. That was nice. So yeah, that was a good thing. Whew. So what does it mean for my fxy and my fyx to be the same? And I'm trying to remember. I think that's actually in another chapter, like not right now. I think it's later, where it's called a name. I almost want to say it's like harmonic or something, but I don't think that's it. Yeah, like equivalent accelerations, because they have yeah, gosh, what is that? I'm gonna go look it up. I don't even know if it's covered in this book, but I know it was somewhere else. Or y'all, can I just, do you mind real quick? I'm gonna search it. I'm gonna search it. What is the name of a function where second partial derivatives x, y, y, x are the same, and it's gonna be like AI blah blah blah. Isn't there like a no? I mean, it'd have to just pop. You know what I mean? There's like a name for it. I don't know. We'll look it in. I'll try to figure it out later. That's your homework. Go look it up. But there's something special about it, and it might be later. I can't remember. It might even be on the homework. I just didn't see it. I doubt it, though. Okay, cool, good. Moving on. But yeah, there is something special about this being the same as that. I just can't remember the name. Moving on. Good to go? Okay, everything will be much easier now. Maybe. So chain rule, it's well, we think chain rule is when you do that little arrow thing. So just like we were doing a few seconds ago, right? We did this, and I said, derivative of the inside, and then you did something like that. Chain rule, right? Yeah. So this chain rule is not exactly like that. I would say this is closer to implicit differentiation than anything. So I'm going to say this is similar to implicit, but it's not the same. It's just the same feeling. Notice here on this derivative, and it's really archaic, but you have this guy here is actually all just fx, and then what's the derivative of the inside is x prime. And then you have this big thing here. Again, they're putting way too many letters. It's fy. And what's the derivative of the inside? Would be a y prime. So essentially what they're trying to say is you got this guy now. You have these chain rules this way. Okay. Now we've been doing chain rule forever. But now they're trying to use letters. And if you just see the top formula here as like an example, notice that we have all D's. But if you keep going a little bit further, we have D's and del's all mixed in. So I would almost say like this is a partial derivative, and this is like a full derivative. And I don't want to use that term. That is not a real math term. But like, it's kind of what's going on. It's like, it's a regular derivative. Yeah, but again, we already proven that partials are the same as regulars. There's no difference in derivatives. It's just that it's singular almost in a way. It only has the one variable instead of the other one has like multiple things. Now, this thing right here is totally confusing. I have no idea what this means. I've seen it. If you can decipher it, cool. You know, like some people, they do this thing with the factoring, or they do this number. Do y'all know what I'm talking about? To factor? No? The box method. Do you do that? Oh. Okay. Well, this is similar. We'll call it the diamond method. And I won't use it. I just won't. There's no need for that, okay? This is all very handy stuff. It looks great. Pause. This is important. This is important. That's actually super, super, super important. These guys are okay, but this one's super important. It's just a formula where we took our partial derivatives and moved them around to make it a little cleaner. But dy dx, which is something, this is literally a slope, okay, is equal to this stuff. And if you just take your first derivatives of whatever, pop them in, you're done. Very simple formula. And we will use that today here in a few minutes, okay? Basically, it takes all the complexity and goes bloop, and you're done, okay? But don't worry about it right now. Let's do the first problem. This one may be nervous. But it's actually a very good introduction problem, really. So, blah, 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 find dw dt. Okay, and the hardest part about this in my math lab is that it has to be in terms of t, where with WebAssign, you can just literally toss whatever letters you want, and it was great. So, like, it was so much easier there. This one here, it's not that much worse, but with just an extra one step. I need to find w prime, essentially. W prime. And this is my w. Without going too crazy, there's my w. So I'm going to go through the motions with you. I'm going to rewrite w, and then I'm going to do the w prime. I can't remember. No, in fact, I know. I have not taught Cal 1 in many years. So none of y'all had me for Cal 1. When you learned implicit differentiation, did you use primes? Did you use D's? Did you do dy dx? Dy dx? Okay. And that's what you had to? You were okay, so I'll do that. I'll do that style. I have 3 different implicit styles, but I'll do that because that's actually proper. So we'll do that. Okay, so I want dw dt. Okay? Basically, I'm saying w prime if you want to make it like cleaner. But let's keep going. So z will go to dz dt. I'm thinking implicit here, right? What's the derivative of z? It's z prime, or dz dt. What's the derivative of my sine? Goes on. And I leave the inside alone. Everything's happy. But then I have this, I guess, chain rule. I mean, this whole thing is called chain rule. But we have that, regular old chain rule stuff. But this would be a product rule, wouldn't it? Because I have 2 different things multiplied. Again, think implicit for a little bit. Think like implicit. Every single thing is important. So derivative of the first would be dx dt times a y plus, and then you take the derivative of the second one. So you say x times dy dt. That's your answer. What? This is that dy dx implicit format. Y'all didn't have me for Cal 1, so I couldn't have taught you anything else. If you don't mind, I would like to show you like the primes method and then the D method, I guess is what I call it. I call it flags, but it's fine. So I'm going to literally recopy what I have here. And I think it'll be a little bit cleaner, but that's up to you, okay? So what's the derivative of z? It's z prime. Just call it what it is. Sine goes to cosine. And then now I have a product rule here. And so you can say x prime y plus x y prime. And at least at minimum, it's smaller and it's not as complex looking. So that's the prime method. That's my personal one. It's nice. It's clean. It also is very easy to get something wrong because you miss a prime and it's all over. So that's another little side effect. Okay. But either way, are y'all kind of seeing what I'm doing implicit wise, right? When you think implicit, I have to account for every letter, right? Every little variable. Okay, but now I go back and say, well, these guys, I'm going to plug them all in. I want to plug in, when I see an X, I plug in an X. When I see a Y, I plug in a Y. But then I don't have just that. I have X primes and Y primes, right? So here we go. I'm going to use a different color. And I'm going to look at each one of these individually. Let's take X is 3t. So X prime, or again, you could say the dx dt, either way. What would that be? What's my derivative? 3, yeah. Just 3. And so in a few minutes, whenever I see an X or an X prime, I'll plug those guys in, right? I just literally plug it in. Because this is my answer. I just have to plug it in now. Okay, let's look at the Y's. I use different colors, so it's fun. Now for my Y's. So Y is equal to ln of t plus 6. So what's Y prime? What's my dy dt? Perfect, perfect, perfect. Derivative of ln is 1 over stuff. And the derivative of the inside just a 1. So we're good. Perfect. 100%. One more color. Wine colored. This guy. So I got my z. And so I'm going to do z prime, or again, dz dt. What's the derivative of e to the something? So here the same thing, right? Cool. What we have is everything we need. Like, we have all the components. Like, doesn't go away over there, man. Go away. Oh, no, go away. Okay, good. So I'm just going to plug them in. And you can use different colors. I don't know, but like my greens, my oranges, my wine colors. I don't know. So my z prime, I'm looking around. Oh, there it is. I have that. Cosine of x. Oh, there it is. I have that. Times y. Oh, look, I have that. I'm doing that on purpose, by the way. I know it's annoying. Sorry. X prime. Oh, boom. Y. No, we're done here. This. Well, yes. Eventually, we need a number, but the algebra side is done. Well, calculus side is done. X. There it is. 3t. And then I have a y prime. Boom. There it is. Done. And we're done. This is what you type in that box. We're done. As in done. So I want to just make sure that you're okay with the style here. There's two derivatives. I'm being very careful with each one of them. When it says derivative, I do derivative. But then I also have all the originals that I'm going to plug in. Mush together and you're done. Yes? What are you thinking about this? It's okay. Go ahead. Okay. So what is the use of this, right? And a lot of the calculus 3 actually does have a use eventually. We're finding the derivative of w. That's simply it. We're just saying, what's w prime? What's my slope of w? But then we just have a lot of complicatedness, right? And so I have to say that what I just did was the proper way to do this. I want to show you the improper way here in a second, but let's finish this up. We got t equals -5. What do we do with that? Yeah, plug it in. Plug it in. Boom, 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 and you're done. So I'm just going to show you the answer because, well, that's easier than using a calculator. So there, and you can see I did it before class because I was nervous. I want to make sure, do I actually know what I'm doing? There's one small thing that I was noticing. They have a 3 in the front right there. And what they had done was they took the 3 and this 3 and they factored it out to the front like that. Everything else is the same. This T here, it just put it on top. But everything else was a copy paste. So there you go. Cool? Huh.
I was working out like, why did they get a different answer every day? Instead of like a t equals 0 instead of t equals -5. Like
That changes everything.
just a little bit, just a little.
So when we have functions with a whole lot of different variables, a lot of different functions for those things going on, then this kind of mushes it all together into a single slope, single rate. What I used to, I don't think I have this as the lab anymore, but I used to have one lab where it was like rocket fuel versus weight capacity versus this and that. So your rocket's going to burn out, which actually lessens its weight over time, right? But then you'll have more like a constant energy when you're doing it. You got all these different variables kind of mushing together. How much do you need to make it go? You know what I mean? So, or how fast is it going at any time? Is it okay if I show you the wrong way to do this? And it's not bad. I mean, it actually gets you the right answer, but you're gonna laugh at it, I'm sure. Yeah, but I'm doing this not just because it's actually much harder, but the reason why I'm doing it is because I want to show. I want to show the possibilities here. Okay. Notice that we have my W. What if, and we're just wanting dw dt, right? What if I just plug them in right now, from the very beginning? And so I would have et plus 5 sine, and then I got a 3t ln of t plus 6. There it is. That's my W. And then I say, find derivative. It really is that easy. But now it's like product on a quotient to a chain and yeah. It kind of gets a little, But it is possible, and I'm going to attempt it right quick. T plus 6. And then derivative of this thing is a product rule, so I'd have a 3 ln t plus 6, and then I have a 3t derivative ln is 1 over stuff, and there you go. It actually wasn't that bad. There's your answer. So could you plug it in the very beginning? Yes. Should you? Oh yes. Oh yes. That's why they don't teach it this way. Yes, yes. Or here's another one. What if Desmos or some equivalent can do derivatives with one variable really well, right? So you just plug it all in, and it's like a big mess, and it goes floop, and it gives you the answer, right? I don't think a nice calculator can do what we did right here. They don't understand z primes and stuff, right? It doesn't understand, but it can do one derivative real quick, right? So it's just a different method, but either way has its merits, I guess. Cool? Okay, so not required for that. I just wanted to kind of show an alternative option. So I want y'all to do this one, but actually, it's different. So, what it is, if you kind of look around, if I said, hey, look at this guy here, take a derivative, I would hope you would think implicit, right? Because there's really no other way around this. We are doing implicit differentiation all over again. But here's the thing. Scroll on to the next one. See how, well, no, that's different too. I wanted to have y'all do one. How about y'all try it? Y'all try, do it implicit or not, do whatever you want, and we're gonna figure it out. Just attempt it. This is old school. This right here, that doing implicit, that's Cal 1. You just had that like 2 days ago.
Oh, yeah, totally not a year ago.
Totally not a year ago. Do y'all do implicit in Cal 2? I can't remember. It's been a while, right? Oh, perfect. Perfect. That's why we're here in Cal 3.
It was a bit hard to do that math for all those years,
Yes. Yeah. And it's hard to see your work now because the water, bled the ink out. Yeah. Oh. We had been doing it just the last problem, so it's very, very similar. I feel like I should start. No, I can't. I'm gonna just be patient. So like off mic. I truly feel like it's amazing that I sound as like confident as I am. Because I go in here every day thinking I'm gonna mess it up, and I do. I still make mistakes, but like I called it out. Didn't I say implicit earlier? This is literally a Cal 1 problem. I mean, it's a tiny, actually, probably about the size of a Cal 1 problem. But I said, oh, I don't know. I just think it's because it's a fun class. And you guys are fun too. Let's do like one more minute. I have the formula book here. I wonder if I wrote something in here about that that partial derivative stuff being the same. Yes. Okay, I think I was off by a little bit. If it's the first partial derivatives that are the same, then it's something, not the seconds. I'd have to go back and check, though. I still thought it was this first, though. Okay. Y'all good? Or at least ready for me to do it, I guess? Did you get an answer? Perfect. Perfect. Me neither. So I'm going to go through the list very slowly. So I need to take the derivative in terms of x. And so that right here would be, what, a 6x, basically? Easy enough. But again, I have to be super careful. And I would like to do dx dt here, which to me is a little overkill. But you could also do x prime, because I'm trying to do that. What's the derivative of x? It's x prime. Everything else applies. Just keep that extra little flag, and that's what I say in Cal 1. It's like a flag, just saying, hey, I took a derivative. Okay, I just took a derivative here. That was just a reminder. X times y, product rule, right? So let's leave the first, take the derivative of the second. Derivative of y would just be a 1. But remember, oh no, I took a derivative in terms of y. And then 1 took a derivative in terms of x, multiplied by y. This one here, this is easy. Take the derivative. What do we get? Yeah, 4y and then y prime, yeah. dy dt, or whatever you want to call it. 13 goes to a 0, and it's equal to 0. So yeah, I want to use the primes personally. So this is x, this is x y prime, and this is y x prime, and this is 4y y prime. So you can see how much cleaner it looks with the primes, right? Not required, but it's still pretty cool. Another way, and I've really not done this in a long time, but if I were to take this derivative in Cal 1 implicitly, I think it's just 6x, and then you take the derivative of the x to make just the y, so it's like a 1y, and then you have an x, and this is where you put dy dx, and then you got a 4y dy dx equals 0. Because like you leave the x's alone, right? But then the y's are the ones you do something about. Yeah, and that's fine too. That totally is legitimate, because if you notice, that's exactly what we're looking for, right? So there's no need to convert. There's no need for like DTs or anything weird. You're done. So then you just factor that out and you're done. In fact, I kind of want to finish that one because it's so nice. I want to factor these guys out over here, and then I'm going to move all of this chunk to the other side. So dy dx times x plus 4y is equal to a negative 6x minus y, and then I divide and I'm done. So that was way easier. Why didn't you do that, Chad? There we go. It's because I just wanted to show different methods, but here, I'm going to keep cruising with this guy if that's okay. I want to get, ultimately, what's dy dx is y prime over x prime, essentially. I'm saying d as in like delta. Yes? And so like the alternative method of this, and maybe I'm just overloading y'all with terminology. I'm so sorry if that's the case. Like you pick one road and you're fine, right? But that's the D method, which is nice because now I got, oh, well, I need just dy over dx. So then you get your dy's, you get your dx's, and you mush them together. So dx would have a 6x plus y, and your dy's would have x plus 4y. And you can see the similar results. Move this guy over, and then you're going to divide on both sides. That's a negative now. So divide by dx, divide by this guy, you get the same answer right there. I don't want to overload you. I really don't. But I just want to show the possibilities that there's other, maybe you won't like this, maybe you like that. I don't know. Okay? What are you all feeling? You feeling like, Chad, you're doing the same problem 5 times, Chad. Like, just pick one and go with it, dude. I know, but but like here, I'm gonna the Cal 1 version where you have your x's are left alone, derivative y dy dx, right? So it's Cal 1. You like it? It's a lot easier, isn't it? Especially for what we're asking for. They're asking for it. Might as well. Do y'all like the flag methods? Yeah. The D's. You like that? Yes. Yeah. To me, that's also the case. I like to say, oh, I took a derivative of x, so derivative of x. It's a flag in a way. I'm saying, hey, look at me, look at me. And then I can just separate it and then divide and I'm done. So it's a little bit more algebraic, I guess you can say. But ultimately, though, we're not done because what do they want us to do? There we go. So when I plug in x, y coordinate, x is 1, y is 2. Negative 8. Oh, really? And that's 7? I got 8 over 7?
That's my bad. It would be
8 over... Oh, 8 over 9, you're right. Gosh, we do all this and I can't even add 2 numbers, you know?
It goes too long, Chad. You can't do that.
8 over 9, there it is. Negative 8 over 9. Cool. Not too bad in the end. Now, can I tell you that all of this was a waste of time? Because there's a formula. Oh, do you remember? I had said, look at this formula, it's super important. And look, it's even asking for the exact thing I was looking for. So I want to show you the formula. I'm going to use it on the instructor side and just show you just how easy it is. It's so much easier. So it's fun. It's great that we're doing this. I'm wanting to show you the possibilities. But ultimately, if there's a formula, I think we should use that, especially when it comes to exams. Now, the one confusing thing about this formula is that it's x over y. Did you see that? It's x over y and negative. So just watch out for that. What it's doing is this actually is the reciprocal. The like literally it's perpendicular to one another. The negative reciprocal is perpendicular. But blah 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 blah. Let's just do the formula. So I want to do negative of the derivative in terms of x. And I mean keep it as easy as possible. Derivative in terms of x, what do we get?
X, that'd be 6.
6x, easy enough. Very simple. Y, 0 and 0. Derivative in terms of y. Let's start here. 0 again. Derivative in terms of y. X. Exactly. Derivative in terms of y. Yep. And then finally, perfect. And if you mush it together, or if you distribute, I guess, look, bam. That was so much easier, Chad. So much easier. I know. So much easier. Does this formula apply to other situations? I would say, yeah, as long as you got 2 variables and you're looking for this specific style. Doesn't have to be x and y. Just be careful though. Cool. We only got 9 minutes left. Oh my gosh, it just goes so fast. Let's go look at the next one. So, yep, I definitely see it. I see it. They're trying to make it more complicated by using different letters, but this is identical to the first one that we were doing. This is our function, and then you could just plug it all in. I mean, that's one way to do it. But I think that it's easier just to take all of my separate derivatives as we go. So, we got 9 minutes, 8 minutes. I think we can do this. Unless y'all want to do it, then I can wait. No? Okay. Exactly. So, I want W prime. Actually, no, they're not asking for W prime. Do you see what they're asking for? And that's a partial, meaning we're only doing like one variable of the two. Essentially, we are ignoring S in a weird way. We're going to have to plug it in still, but it's like W in terms of R, W sub R, I guess. Kind of weird. But that shouldn't deter us. So here we go. DWDD? No. We don't have any T's. I'm going to say W prime. Do you mind if I get it? Let's do it rough. W prime, just take a derivative, man. Derivative of this power 2. What do I do with that? Awesome. Now to the 1 power, derivative of the inside. Love it. And I'm going to get rid of that 1 power because it looks like a prime. And there it is. We just took our derivative. Boom! And now all I have to do is just plug them all in and we're done. Literally, that's all we have to do. It's super easy. Except, there's always a little caveat. So let's start with the x's now. So x was equal to r minus s. And now I'm wanting to find x prime. And you know what? You're right. It is a 0 in the end. So yeah, r would be like 1, s would go to 0 because we're only looking for r. But that really, it hurts my soul. Because what if they ask for the next one is this dude right after it? It's an s, right? Then I have to go back and do the whole thing over again, right? So what I do is I'm using kind of like my prime flag method thing, and I'm going to knock them out later. So just to be as silly as possible, this is 1 r prime minus 1 s prime. And you don't need the ones. You don't need the ones. I'm just kind of like showing that it's like, what's the derivative of r? What's the derivative of a single letter? It's 1. But we need to keep that prime in there. For y's, I start with a cosine. Derivative of cosine? Negative sine. Leave the inside alone, and the derivative of the inside would be r prime plus s prime. So we're replacing primes with more primes. It's just going to be so weedy. But that's, I mean, I'm trying to keep it the easiest as possible, really. The prime method is the quickest. Derivative of sine. Leave the inside alone. And derivative of the inside would be? Yes. Yes. Where is a number? Give me a number here. Though there's a 2 in the front, so I guess. That's all that's all we got. So I am actually going to plug them all in one by one by one. So here we go. I've got r minus s. Ooh, that one's an easy one because it's just cosine. If you want to. We will eventually have to do something like that. Yes, that's your call and win. I'm being stubborn right now and just leaving it alone. X prime is r prime minus s prime. Y prime. Give me a second here. It's a minus sign. It's a plus. And then finally, cosine r prime plus s prime. Wow. Let me make sure that, like, this is big parentheses here. And this is big parentheses here. Just so that we know what we're doing there. So, the main idea at this point, I know we only have 3 minutes, but that's plenty of time for this thing. The main idea is that we're only looking for the derivative in terms of r. And that means that my r prime is equal to 1, and my s prime is equal to, we already said it, 0. And so anytime you see an s prime, you can just knock out whatever's next to it. And whenever you see an r prime, just leave it, make it a 1. And so that makes it very, very simple going forward. But having this written out is going to help you for finding DWDs, which they will ask for. I mean, is that on the next question where they want both? Look, right there. Perfect examples. The next question is going to be just like that, where you need both. So it's good that we do this ahead of time, so you don't have to work twice. So this guy here turns into a 1. This guy here turns into a 0. This guy here is a 1. This guy is a 0. This guy is a 1. This guy is a 0. And you can see that most of it is still retained. So this is literally W sub R at this point, not just prime. So 1 minus, and then I'll only have the sine times 1, so that was easy. And then I have a cosine times 1. And at this point, all I need to do is plug in my two numbers and we're out of here. Here, I'm going to circle these guys. That's kind of what I was doing over here. Colors. I want to pull up Desmos, but I'm just going to trust myself. I probably shouldn't trust myself. In fact, Desmos Scientific is actually really nice with this stuff. I just want to be able to have y'all see it though. So let me control minus so we can zoom out here a little bit. And I'm going to try this. So R is equal to 7, S is equal to -7. 2 times 1 minus S cosine R plus S radian mode. Right? Because I'm going to totally get it wrong here in a second. R plus S cosine R plus S. Oh, well, radian degree apparently doesn't matter. That's kind of nice. So we got it. Perfect. Plug it in, we get a 60. Welcome to Calculus 3, where we don't have very many numbers anymore. Yes, distant memory. I love that. Okay, we're good. We're done. That was it. I'm going to stop the recording, but I can leave that up here, so.